All right, we are finally to 2019's free response questions, doing number 1 and 2 today. So this is the questions that my kiddos last year, my first year teaching Calc, took. I think the questions are pretty doable. Um, Number 1's pretty good. I think it's a good question. Practices everything that we've learned. So first Calc active problem. So let's go ahead and jump on into it. Um, Number 1, it says that fish enter a lake at a rate modeled by the function e given by e of t, which equals 20 plus 15 sine of pi t over 6. So it gave us a rate in problem right here. So this is rate in. It's telling me a function for the amount of fish that are coming in, the rate of the fish that are coming in. It says fish leave the lake at a rate modeled by L of t. So here we got rate out problem. All right, and since this is Calc active, I put rate in for y1, and I put rate out in for y2 into my calculator. They're measured in fish per hour, and t is measured in hours since midnight at time equals 0. And it says how many fish enter the lake over a 5-hour period from midnight to 5 a.m. and give your answer the nearest whole number. So it says how many fish enter the lake, so we need to do our rate in function only, nothing to do with our rate out. So simply it's just going to be the integral 0 to 5, 0 to 5 hours of the rate out, or I'm sorry, rate in, which is e of t dt. And I plugged that into my calculator again as y1, and I typed that in exactly like that into the integral, and I got 153.457 blah 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 blah. It says to the nearest whole number, so that would be 153 fish. 153 fish enter the lake over a 5-hour period. Not too bad. All right. Part B says, what is the average number of fish that leave? Okay, so average fish that leave the lake over the 5-hour period from midnight to 5 a.m. All right, so average and leave, we're going to do average value, which is 1 over 5 minus 0, integral 0 to 5. And I just want to know the average fish that left, so we're just going to use our rate out equation. So that's going to be L of t. And again, this was my y2 in my calculator. I typed it in exactly like that, and I got 6.059038. So that is 6 fish per hour. I wanted to know the average number of fish that leave per hour, so that's 6 fish per hour. On average, leave my pond. All right. A and B were not bad, as long as you knew average formula, as long as you knew which formula to use. I mean, it wasn't too terrible. Okay. Now let's talk about C. C says fish enter. Okay, wait, sorry. C says at what time t between 0 and 8 hours is the greatest number of fish in the lake? All right. It wants to know the maximum value over a closed interval. So that's when we need to consider the endpoints and the critical points. Okay, well, how do we find the critical points first of all? Well, in this type of problem, I always want to have an amount equation. So I'm going to say A of t, which is the amount of fish in lake at time t. Okay. I'm going to say, remember how rate in, rate out problems work for amount? It's always the initial amount. Oops. It's always the initial amount plus the integral, 0 in this case is our initial time to x, of my, or I'm sorry, t, I don't know why I said x, 0 to t, of my rate in, which is e of t, so I'm going to say e of x, since we've already used t, minus L of t, or L of x dx. Okay, so that's the formula, right? Now this isn't so much important for part C, but it will be for part D. Here's the thing though, like we have this, we have the initially we start off at midnight, but if you notice at midnight it does not tell us initially how many fish we have, and there's really no way to figure that out. We don't have an initial value, so we're just going to assume that it's zero. We're just going to assume that there is no initial amount. Okay, so if they don't tell you an initial amount and there's no way of finding an initial amount, we're going to assume that initially there's zero. Okay. But regardless, in this problem, we need to know a prime of t, and that would get rid of the initial value anyway, so it doesn't matter for this problem. And then a prime of t is just going to be rate in minus rate out. That's it. So we need to set that equal to 0. Okay. So to solve for my critical point, so actually what I did in my calculator is I did, E of t equals L of t, solved for that. And in my calculator, I found the intersection of y1 and y2 between the intervals 0 to 8. So I found that, I just graphed it, and I just found the intersection between 0 and 8. And I got that the critical point was time equals, what did I get? 6.2035644. So that's what I got for my critical point. So now, excuse me, in order to figure out my my maximum, I'm going to do my little chart here. T and A of t. And this is kind of what I was talking about here. Like when I'm trying to figure out the maximum value, like we have no initial value to add at the beginning, so my A of t equation is just simply the integral 0 to t of e of x minus L of x. So 0, we just assume there's 0 fishes. I mean, it doesn't really tell us anything otherwise. Okay. Then we're going to do it at 6.203, and we're also going to do it at time equals 8, the endpoint. All right. So again, I plugged this box here into my calculator, and I did y1 minus y2 in the integral, and I did 0 to 6.2 and also did 0 to 8. All right, so I plugged my input in for t, and I did y1 minus y2 in my calculator. Okay, so for 6.203, I got 135.0149199. And for time equals 8, I got 80.9199773. So on the interval 0 to 8, the maximum, it says at what time, it didn't say what the max value was. So the max occurs at time equals 6.203, blah, 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 blah. Okay. So there's your answer. And there's my justification, is the fact that I found the critical point, all right, by taking the derivative of my amount function and setting it equal to 0 and solving, and then I check my endpoint. So that's all the justification you need. All right. All right. And then lastly, D says, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m.? And explain your reasoning. Well, simply, rate of change is equal to a prime of t. Remember, I hate when math does that. Remember that we defined a in the previous problem, so we know that rate of change is a prime of t, and we know that that is equal to e of t minus L of t. So it wants to know, is the rate of change in the number of fish in the lake increasing or decreasing? So is the rate of change, so we're going to set that equal to 0 and solve. So hold on 1 second. And I realize now I just misread it, because it's not asking is the number of the fish increasing or decreasing. It wants to know, is the rate of change increasing or decreasing? So the rate of change is equal to a prime of t, which is e of t minus L of t. It wants to know, is this right here increasing or decreasing? Well, how do I determine if that's increasing or decreasing? I'm going to take this equation and take the derivative of that. To determine if a rate of change is increasing or decreasing, we see if the second derivative is positive or negative, right? Because it's not, again, it's not asking is the number of fish increasing or decreasing. It's asking is the rate of change increasing or decreasing. So we need to look at the derivative of this at time equals 5 and see if it's positive or negative. So the derivative of that is equal to e prime of t minus L prime of t. Okay. So then if I do time equals 5, I get, and again, I did this in the calculator. I did the derivative of the e equation at 5, or I did the derivative of y1 at 5, and I did the derivative of y2 at 5, and I subtracted those answers, and you get negative 10.7228, which is less than 0, so therefore it is decreasing. All right. So not too bad at all. That kind of tripped me up a little bit in the reading. I kind of had to second guess myself. It's the rate of change increasing or decreasing, not the amount of fish, but is the rate of change. So we had to kind of take it a step further and discuss the rate of change equation, take the derivative of that, and see if it's positive or negative. That's how you talk about increasing or decreasing of anything, is look at the derivative of it and see if it's positive or negative. Okay. All right. So that does it for number 1. Here's the answer key here. We did the correct integral, and we got the answer to be 153. We did the correct integral, and we got the answer to be 6. So A and B were 2 simple integrals, and that was fine. In C, we did set the derivative equal to 0, e of t minus L of t, to figure out our critical point. And they had this whole discussion right here, but they did not consider the endpoints in the first part. So I guess that is because of that whole initial thing, but this is the way we did it. We considered a of t to be that function, and we took the derivative and solved for the critical point. We checked our endpoints as well, and we got that it was at time equals 6.204. So that was the box right there. That was how we did it. And then D was the fact that we considered E prime of 5 and L prime of 5, which was that right there. Got that it was negative and said, oh, it was decreasing then. Okay. That's all it is. So number 1 wasn't too terrible. We've seen those types of problems before. Now, number 2. Number 2 is a polar equation, and again, that's not on our exam anymore, so you don't have to stress too much about this one, but I would like for you to follow along. And letters A and B, I think, are extremely doable for this. Letters C and D, in my personal opinion, were the hardest problems on this exam, not because of the math, but just because of trying to figure out what they were asking. So let's see if we can do it. It says, let S be the region bounded by the graph of the polar curve, and that is an ugly looking polar curve right there, but we're between 0 and square root of pi. So here we're at 0. We traverse all the way around until we get back to the same spot at the square root of pi. So 0 to square root of pi gets you all the way around that one little loop. And in my calculator, I graphed this. I graphed this into my R polar equation, and I just looked at it between 0 and square root of pi. If you don't look at it between 0 and square root of pi, it's a whole mess of stuff. So you just want to look at that first petal. But anyway, find the area of S. It's not too bad at all. We know the area equation is just going to be 1/2 integral a to b, in this case 0 to square root of pi, and just my r squared. So r of theta squared d theta. And again, I plugged this into r1 in my polar menu, where you could have done it y1 if you really wanted to, but I did r1 and just solved that out, and I got 3.534292. That's all you had to do, is just use your area formula. So part A should have been a gimme point. Part B says, what is the average distance Okay, so here we go. Average, first of all, average is going to be just 1 over b minus a, so 1 over square root of pi minus 0. So there's the average part. And then average distance from the origin to the point on the polar curve. So it wants to know the average ones of these. What do you call those lines? Those are just radiuses. It wants to know the average radius length on this curve. So it wants to know the average value of this function right here. That's it. All we have to do is do the average, which we did that part, a to b, 0 to square root of pi, of my radius function. So just r of theta d theta. That's it. That's all you had to do. Find the average value of my radius function. That a radius, by definition, is the distance from the origin to a point on the polar curve. Okay. And in this case, I got, if I can find it on my paper, 1.579933 to be the average. Okay. A and B, if you know what it's asking, pretty self-explanatory. Okay. So I think A and B were pretty good. Now, part C. Part C was confusing. All right, I struggled with part C, so I don't hold it against you for struggling with this. If you got it on your own, that was awesome. I struggled with C. C says, there is a line through the origin with a slope m that divides the region S into two regions with equal area. So basically what that's saying is we have this line that intersects right here. We have this line right here that cuts it into two equal areas. And that line, it doesn't tell me the theta value. It doesn't tell me what this angle measurement is. It just tells me that the slope of it is m. Well, it says, okay, write but do not solve an equation involving one or more integrals whose solution gives the value of m. So this is the way I'm thinking about it is we need to know what this m value is. We need to know what this slope is in terms of theta, because then I can have an integral from 0 all the way up to theta. That's what I need to figure out. So right now I know the slope is m, but I don't know what the theta value is. If I can figure that out, then I can make my integral no problem. Here's how it works though. This theta value, or this slope, is just rise over run. So you can think of us going over x and up y to this point. Okay. So m is just equal to y over x, right? The slope is just equal to y over x. It's rise over run, right? Well, how do I figure out theta when I'm given x and y? Remember, this is theta right here. It's that angle measurement. Well, if you think about theta, that's just, we have the side opposite and adjacent, so that's tan. So I know that the tan of y over x, or I'm sorry, I apologize. The tan of theta is equal to y over x, which is equal to m. So I know that the tan of theta is equal to m. So if I want to get theta by itself, I know that tan inverse of m is equal to theta. So that's how we relate theta equal to m, right? So I know that this angle measurement here is equal to the tan inverse of m. That was the tricky part for me, having to really try to think about how we can get theta to be m. Now the integral is easy. The integral, I'm saying like, all right, I'm going to have 0 to this theta value, which is 0 to tan inverse of m. So the area of that is 1/2 the integral 0 to tan inverse of m of r of theta squared. I know that that's half the area of S. So I know that that's going to be equal to half the area of the entire thing of S, which is 0 to square root of pi of r of theta squared d theta. Which in this little bracket here, we found this answer in part A. So if you would have put the answer in part A and halved it, that would have been fine as well. This is the big part we had to come up with. And all you had to do was set that equal to half the area from A. That's the answer. That whole equation is the answer. Just solving for that m value, that was tough. Okay. And then lastly, D. D says for k greater than 0. Okay, now you're going to have to work with me on this one, and you have to have your calculator to see this. For k greater than 0, let A of k be the area of the portion of the region S that is also inside the circle R equals k of theta. So for instance, okay, let's give an example. Let's say that k is equal to, R equals 5 cosine of theta. Let's say k is equal to 5. Well, we should know what 5 cosine theta looks like, or you can graph it in your calculator if you don't. But that's just a rose with a petal, one petal, and it has a radius of 5, or I'm sorry, a diameter of 5 on the x-axis. So it looks like this. It's just a circle, right? That's just a circle equation with a diameter of 5. Looks like that. Now, let's say I decided to make that a little bit bigger. Let's say I decided to make this 10. So then what it's going to look like then is this. It's going to be a circle. So I'm going to go all the way over here to 10. That's going to look like that, right? And the A of k is the area that is shared by S and that piece of the circle. Now, what it says is it wants me to find the limit as k approaches infinity of A of k. So what that's saying is it wants me to find the area whenever k is at infinity. That seems kind of weird, right? But if you keep graphing bigger and bigger numbers for k, here's k is 5, here's k is 10, here's k is 100. And as k approaches infinity, eventually that circle is going to be encompassing the entire right side of the y-axis. That's what happens whenever k approaches infinity. If you don't believe me, keep typing bigger and bigger numbers in for k into your equation, k cosine of theta, into r, and it's just going to keep becoming a bigger and bigger circle. So what that means is, and it's kind of hard to picture a circle that has an infinite diameter, but that's going to eventually encompass the entire right side of the y-axis, which in terms of the overlap with the area S is this area here. So if I want to know that area, that's just the area from 0 all the way to the other part of the y-axis, which is at pi over 2. It wants me to know that area of S, excluding the part to the left of the y-axis. So simply put, that limit is equal to, so the limit as k approaches infinity of A of k is simply equal to 1/2 the integral 0 to pi over 2 now instead of the square root of pi of r of theta squared d theta. That's it. That's the connection. That was hard. That was a hard concept to understand, but it really wanted you to understand that as k is getting bigger, it's eventually just going to be exactly on the y-axis, and that's a huge infinite circle. Okay. So if you type that in the calculator, you get 3.324470722. Okay. And that's it. That's all you had to do. That's the answer. That's the area I was looking for. When that infinite big circle, the region it's overlapping is this S right here. Okay. And yeah, that does it for number 2. We're at 24 minutes. So number A here, we got the integral and we got the answer. Okay. The integral and answer for B. So it's just 2 integrals and 2 answers. For C, it wanted us to equate the polar areas using inverse trig to figure out what M was. So knowing that theta is tan inverse of M, it wanted that. And then it wanted the equation that we came up with, that half of the whole area is equal to the area from 0 to tan inverse of M. And then lastly in D that we get, it's only 2 points for that, the limits of integration. So the fact that we knew we were doing 0 to pi over 2, and then the answer was 3.324. Okay. All right, so that does it for question 2 and 1 for 2019. We will do 3 and 4 tomorrow. So, good job, guys.